Let's get started with this example. Here we have a vacuum tank that's being evacuated by a vacuum pump. So this is a very realistic, kind of a real-life example. You've got a vacuum tank here. There's a vacuum pump, and the purpose of the vacuum pump is to pull the air out of the tank so that you create a very low pressure vacuum inside that tank. And then what's done in reality is that there are these lines that connect to this tank, and this line would go to suck up, liquids or dirt or things like that. Because the atmospheric pressure is higher, it pushes the liquid, for example, into that hose, and then it would fill up in the tank. So they use these a lot in construction sites and clean up things, sewers, etc. And a schematic of the process is shown down here. You have your tank. It's connected to the pump via a valve, and then you have a valve here with the hose. So what happens is the tank, in this particular case, we're given the volume of the tank. It's filled with air at 1 atmosphere and 70 degrees Fahrenheit. Notice that we're using English units in this example. Now in ME200 recently we've stuck with SI or metric units. This one I'm using English units instead. All of the analysis is the same. It's just when you do the unit conversions, it's much more of a pain to do it with English units. So don't get hung up on the units. Just really kind of follow the analysis in this example. So we have this tank. We're given a certain volume for it. We're told that the air in there is at a certain pressure and temperature. And then it's being evacuated by a vacuum pump. So this valve is closed, so you don't have to worry about the hose part. This valve is open, and we're starting to pull we're pulling the air out of the tank through the pump. And then the vacuum pump, we're told, is discharging the air into the surroundings at the surroundings temperature and pressure, which are also 70 degrees and 1 atmosphere. So the surroundings are at the same conditions as the tank initially, which again is pretty realistic. You're starting off with a tank that's at atmospheric conditions. We're asked to determine the minimum amount of work required to completely evacuate the tank. So what we want to do is take everything that was in that tank, all that air, and pump it out so that in the end, we're going to assume we have a perfect vacuum in here. In reality, you never get down to a perfect vacuum. That's pretty hard to do with ordinary pumps and such. There's always some very low pressure that's left in there. But for our example, we'll assume that it goes all the way to a perfect vacuum. And we want to find the minimum amount of work required to do that. That might be of interest. For example, if you were designing this tank and vacuum pump combination, often they're gasoline powered, so it might give you some idea on what size gas tank you would need to build into this trailer so that you can make sure you have enough power to do at least empty out evacuate the tank. You of course would probably want to be able to do more than just that, but this would at least give you an idea of the smallest amount of gasoline you would need to evacuate the tank. So that's why this kind of information would be useful. There's one other bit of information here, and that is, note that at the end of the discharge pipe downstream of the pump, so what we're talking about is this location right here, right at the end of the pump, the pressure is the same as the surroundings. So the pressure right at the end here, pressure at the outlet is going to be the same as the pressure in the surroundings, which will be, in this case, 1 atmosphere. That's something that you'll learn about in a fluid mechanics course like ME309, but here it's just given. Okay, so that we know that the outlet pressure is the same as the surroundings. Okay, so to find the minimum amount of work, the first thing that comes to my mind is to use the first law, because the first law involves work. So let's go ahead and try and apply the first law, and we need to apply it to some control volume. So the control volume I'll choose will be one that surrounds the tank and the pump, and it goes all the way to the outlet pipe. Okay, so we'll apply the first law to that control volume. So we'll write out our first law in all its glory. And I'm going to write out, let me start with the rate form of the first law. This is the form that's on your formula sheet. So we'll write it out. all of the terms. And I'm going to write it in terms of the plus the work done on the control volume, or the work that goes into the control volume. In this case, it's power. So let me draw that in my engineering flow diagram. So we maybe have some rate of heat transfer into the control volume, and then we're going to have to put some work in to the control volume to operate the pump. Okay, so that's my energy flow diagram. All right. You notice that this equation for the first law is a rate form. This will give me the instantaneous rate at which we're doing work, or the instantaneous rate at which heat transfer is occurring. You know, the units, for example, that you would have in this equation would be kilowatts, for example. Everything is in units of power. It's rate at which you're doing work. What we want really for this problem is the minimum amount of work. We don't want power. We want the minimum amount of work required to completely evacuate the tank. So we don't care about the instantaneous power. This is more of a before and after kind of problem. We want to find out how much work in total it takes to go from the beginning to the end. So what that means is we want to integrate this equation in time to get a delta. You know, we want the change in the total energy in the control volume. And then the summation term becomes the mass of material coming in with this total enthalpy minus the mass of material that is left with this total enthalpy plus the heat, not the rate of heat transfer, but the heat that has come in plus the work that has gone into the control volume. And really what we're trying to solve for here is the work term. Okay, so we're going from the rate equation to a before and after equation, because we're dealing with a before and after kind of situation. Okay, so that's our first law. Let's go ahead and simplify it, making use of some of the information that we have in the problem statement. First of all, the change in total energy in the control volume, that is not zero. This is not a steady state problem. It's changing with time, right? There's a before and an after. So this is not steady state. Instead, we have a before and after. So let me write this down as delta total energy in the control volume. We, of course, know that that involves a change in internal energy, a change in kinetic energy, and a change in potential energy. We're going to neglect the change in kinetic and potential energy terms. If you're doing it right, the trailer's not flying around changing its speed or changing its elevation, right? It's fixed. So there are essentially no changes in kinetic energy or potential energy. So what we're left is the change in internal energy. And so that will be the mass after, or I'll call it the final state, times the specific internal energy of the final state, minus the mass of the initial state, times the specific internal energy of the initial state. So you can see again, this is a before and after. Here's the after, here's the before. Okay? Well, we can simplify this a little bit further because we know the mass of the final state will be zero because it's a vacuum. There's nothing left inside the tank. So this is zero because at the very end of the whole process, the tank is a vacuum. So I'll just make a note of that so everybody knows that it's a vacuum at the final state. So what we're left with is minus the initial mass times the initial specific internal energy for that term. Okay, so then let's go to the next one. This is the mass times the total specific enthalpy coming in minus the total specific enthalpy going out. So let's simplify that. Again, we're going to neglect the kinetic and potential energy terms. Well, first of all, the mass coming in, we can just make that zero altogether because there is no mass coming in, no mass in, right? There's only mass going out. So the first term There's nothing coming in because there are no inlets. It's all going out. And then we're going to neglect the kinetic and potential energy terms going out. When you're dealing with air, the potential energy of the air is typically very small because the density of air is very small. The kinetic energy at the outlet, that could be significant depending on how small the pipe is and how fast the air leaving that pipe is going. We're not told any information about that, so we're just going to go ahead and neglect it, assume it's small because we weren't really given any information. If the pipe has any kind of a large diameter, those velocities are probably pretty small anyway compared to the specific enthalpy, so it's pretty reasonable to neglect it. So what we're left with in the end is minus the mass that's gone out times the specific enthalpy of the air as it's leaving. So the out there is right here in the picture. This is the out, where the air is going out. All right, let's go on to the next term, the Q in. Q in, we weren't told anything about this. We weren't told to assume that the tank is well insulated or anything like that, so I'm going to leave that in there as a question mark. Okay, because we don't really know. We'll come back to it. I'm going to leave it as a question mark. And the same with the work in. That's what we're trying to solve for, so I'm going to leave that as a question mark. So let's go ahead and simplify our first law using everything that we've written here. So the left-hand side will be mass in times specific enthalpy coming in. The right-hand side will be m out times specific, I'm sorry, I said on the left-hand side, I apologize if I misspoke. It's mass in times the specific internal energy coming in. On the right-hand side, it's the mass out. Let me say that one more time. This is the mass times specific internal energy in the initial state, not in. It's the initial state. I apologize for that. The right-hand side, this is the mass out times the specific enthalpy at the outlet. And then we have our heat transfer term and our work term. And then I'll solve for the work, since that's what I care about in particular. So let's see, this will be work in, this will be, let me make sure I get my signs correct. Apologize here. Okay, so that's what we have for the work in for the time being. We still have some things we need to figure out here. This isn't good enough for us to figure everything out. We need to know the mass in. We need to know the, I keep saying in. This is the mass in the initial state. This is the specific internal energy at the initial state. These we can calculate. The initial mass we can find from the ideal gas law. The initial internal energy we could get from the ideal gas property tables. The mass coming out we need to calculate. We'll use conservation of mass to find that. H out we can find from the property tables. And then Q in, we'll talk about that in a moment, so I won't say anything just yet. Let me first apply conservation of mass to the same control volume. So this is conservation of mass, same control volume. I'll start with the rate form, just like I did with the first law. If I integrate that in time, what happens is the instantaneous rate at which the mass changes inside the control volume, that just becomes a delta M, the change in mass in the control volume. And then the mass flow rate in, when you integrate that in time, that'll just be the total mass that's come in, and then the same sort of thing with the total mass going out. We've already said that the mass coming in is 0, so there are no inlets, so that goes away. The change in total mass inside the control volume, that's going to be the mass final minus the mass initial. And we already said the final mass is 0 because it's a vacuum. So then what we're left with is minus mass initial is equal to the minus mass out, or mass out equals the initial mass. So that's what we get from conservation of mass. So we can make use of that, plug it in right there. Just help simplify the equation a bit further. So let's go ahead and do that. So the work in is now going to be the initial mass times H out minus U initial minus Q in. All right, so I think we're in good shape so far. Let me now, okay, so I'm going to underline that so we remember it. So now, again, I can find the mass initial from the ideal gas law. Let me write that down. So the ideal gas law applied to the tank. The initial mass will be, let's see, it'll be the initial pressure times the tank volume divided by the gas constant for air divided by the initial air temperature inside the tank. So we can find the initial mass through that. So that's not going to be a problem. Actually, why don't I go ahead and just give you the values for that while we're here. You'd have to use the given value. So the initial pressure was 1 atmosphere. The initial volume was 180 cubic feet. The gas constant for air in English units, okay, brace yourself, this looks ugly. It's 53.3533 foot-pounds force specifically, divided by pound mass degree Rankine. And then the initial temperature was 70 degrees Fahrenheit, which when you convert to degrees Rankine comes out to be 529.67 degrees Rankine. And then the 1 atmosphere, when you convert that over to, we'll convert that to pounds per square foot, that comes out to be 2116.22 pounds force per square foot. And so I had to do some unit conversions here. Well, I only really did 2 unit conversions. One was just to go from atmospheres to pounds force per square foot. And the reason I put it in pounds force per square foot is because you see that we have feet elsewhere. And then I did pounds force because there's a pounds force here. And we're trying to find the mass, so that's going to be in pounds mass. And then the other unit conversion was from degrees Fahrenheit to an absolute temperature, which would be degrees Rankine. When you work those, when you work out the calculations, and then here everything will multiply nicely together without any additional unit conversions. The initial mass comes out to be 13.479 pounds mass. Right, so the units work out very nicely. For example, if I do the pressure, that would be pounds force per square foot times the volume, that's cubic feet. In the denominator, I'll have foot-pounds force over pounds mass, degrees Rankine times degrees Rankine. See, the degrees Rankine cancel out, the pounds force cancel out. The numerator, I'll have the pound mass will come to the numerator. I'll have pound mass times a foot, because this, you'll see that the square feet there cancel out with the square feet up there, and then you have a foot. And then there's a foot in the denominator as well. This one goes there. So then you see that you're just left with pounds mass. The only good thing I'll say about English units is that it forces you to do the unit conversions. You can't just guess what the units should be at the end. And I know a lot of people are doing that. I see it frequently on exam and quiz questions where people know that, you know, the answer should be in kilowatts, for example, but they're not sure whether they need to multiply by 1,000 or divide by 1,000. They're not working out the units. With English units, you have to work them out. Otherwise, you're just not going to get it right. All right, so now we have the mass initially. So we just calculated that. The H out and the U initial we can find from the ideal gas tables, where we know the temperature initially, right? So we know that both of these are functions only of temperature. In fact, you know what, let's go ahead and write this out. So we know that H out, the H out is the specific enthalpy as the material is leaving the tank, okay? And we know that for an ideal gas, the specific enthalpy is only a function of temperature. Let me write that down. So we're assuming air is an ideal gas, which means that the specific enthalpy is only a function of temperature and the internal energy is only a function of temperature. So all we need to do is find the temperature at the outlet in order to find H out. Well, if you look at the problem, we're told that everything is isothermal. Initially, the tank's at 70 degrees Fahrenheit. During the process, the tank air is maintained at 70 degrees Fahrenheit, and the surroundings are at 70 degrees Fahrenheit. So everything's at 70 degrees Fahrenheit. So H out will just be the specific enthalpy at T out, which is 70 degrees Fahrenheit. So we can use the ideal gas tables to look up that value. We don't have an Excel, I don't believe we have an Excel table that gives you that value specifically. So what I did is I used the back of your textbook. There's a table in English units, so I just used that one. And it's actually given in degrees Rankine, so you have to convert this over to degrees Rankine, so it would be 529.67 degrees Rankine. And when you look up that value, it comes out to be 126.585 British thermal units, BTUs, per pound mass. I had to do a little interpolation to get that. And you can do the same thing for the specific internal energy initially. That's the U sub I. Initially, our tank is at a temperature of 70 degrees Fahrenheit. Again, 529.67 degrees Rankine. We know for an ideal gas, it's only a function of temperature, so we can use the ideal gas table. And I did that again using the back of your textbook with a little interpolation. Comes out to 90.2753 BTU. That's a British thermal unit. That's a unit of energy per pound mass. Okay, so we're in pretty good shape now. We've got our mass. We've got our specific enthalpy minus specific internal energy. Now we just need to find the heat term. Okay, so to find the heat term, we've already made use of the first law. So, and we don't know the heat term from that. Conservation of mass does not involve heat. The only other tool that we have that really involves heat is the entropy equation. So let's write that out. So we're going to apply the entropy equation to the same control volume. I'll write it down in its rate form just like I did the others. So here's the heat transfer term. And here's our entropy production term. So just to kind of remind you what this equation means, the first term is the time rate of change of entropy inside our control volume. So this is how the entropy in the control volume is changing with time. This term, the first summation here for the inlets, this is the rate at which we're bringing in entropy through the inlets. This next term is the rate at which we're taking entropy out through the outlets. The integral term is how the entropy is changing due to the addition of heat, the rate at which we're adding heat. And then the last term is the rate of entropy production, which incorporates the irreversible effects. So again, we can integrate that in time to give us a kind of a before and after situation. So the ds dt term just becomes a change in the entropy inside the control volume. The mass flow rate times the specific entropy, those just become the mass in times the specific entropy where it comes in at, minus the mass out times the specific entropy where that occurs. So this first one is the entropy that we've brought in through the inlets. The next one is the entropy we've taken out at the outlets. Then we can integrate the heat transfer term. This is just Q in over T, so the dot goes away. And then lastly, instead of the rate of entropy production, it just becomes the entropy produced, or the entropy production. It's not a rate term any longer. We can simplify this just like we did the others. There's no inlet, so that first term goes to 0, so no inlet. And the change in entropy inside the control volume, that'll be the final mass times the final specific entropy minus the initial mass times the initial specific entropy. But we know that the final mass is 0 because it's a vacuum, just like we did in the previous part. So let me simplify this out. We'll have minus m initial times s initial is equal to minus m out times s out. plus Q in over T, and I'm going to come back to that in a moment. This would be T surface plus sigma. So let me talk about the heat transfer term, the Q in T surface. So this is the heat transfer coming in, and this is where the heat transfer crosses the boundary. I say T surface because when I went back up here in my drawing, I drew the control volume to touch the surface of the tank. So it's right on the surface. Everywhere in this case, the temperature is 70 degrees Fahrenheit. You can see it's 70 degrees, and we're told that during the process, the tank air is maintained at 70 degrees Fahrenheit. So right on the surface of the tank, it'll stay at 70 degrees because it's 70 degrees everywhere. There's no temperature gradient anywhere. So it's fine if I just put the control volume right here on the surface of the tank. If we had a situation where the tank temperature was changing with time, then it would be a harder situation. If I didn't know the temperature right at the surface here, what I might have to do, or what I would do, is I would move this control volume to be out into the surroundings a little bit, where I do know the temperature stays at 70 degrees Fahrenheit out in the surroundings. And so that would be the temperature I would use is a little bit further out. And if I did that, then you just have to keep in mind that this entropy production would include some entropy production in the surroundings. It would include the entropy production caused by that the heat transfer through that thermal boundary layer. So this goes back to a previous example in a previous lecture that I've talked about, where you may have to include part of the surroundings if the surface temperature is not well defined. However, in this case, it is well defined, so it's not an issue. We can substitute in for the M out term here using conservation of mass. Remember, if we go back here, the mass out is equal to the initial mass, so I can rewrite that. So let me just rearrange things to solve for the heat transfer. So this will be the following. So let's see, this will be M initial SI, oops, this will be S out, apologize. All right, if I did my, oops, there should be a minus sign here for the entropy production. All right, I'm just double checking my algebra here, make sure, okay, that all looks good. So now we have solved for our heat transfer term. I'm going to go a little bit further on this. Let me evaluate the S out minus the initial specific entropy. Recall that for an ideal gas, the change in entropy, so we'll say S out minus S initial, will be the S naught term, T out, minus S naught at T initial, minus the gas constant times the natural log of the pressure, P out over P initial. Okay, and that's for an ideal gas, taking into account variable specific heats. So this is how we would find our differences in the entropies here, specific entropies. But keep in mind that this is an isothermal process, so T out and T initial are the same. So this term becomes 0 since T out equals T initial. And then if you look at this pressure ratio, P out is, we said, if you go all the way back into the problem statement, it says that, note that at the end of the discharge pipe downstream of the pump, the pressure is the same as the surroundings. So the P at the outlet here is 1 atmosphere. That is exactly the same as the pressure inside the tank. The tank is initially filled with air at 1 atmosphere. So the initial pressure and the outlet pressure are the same. Okay, so P out is equal to P initial. So that gives us a ratio of 1, and when you take the natural log of 1, it comes out to be 0. So this whole thing is 0. So the S out minus SI is all just 0. So that whole term just goes away. So well, then what we're left with, oh, I made a mistake. This should have square brackets there. So then what we're left with is the Q in is equal to T surface times the entropy production term. And there should be a minus sign. Okay. So we can go ahead and make use of that and plug it back into our work equation that's right up here. So we're going to substitute in for that. So let's do that and see what we get. So W in is equal to, apologize, I have to scroll back and forth. Initial mass times H out minus U initial minus the heat transfer term. So this will be T surface times entropy production. I'm just going to go back and double check. Yeah. So this now is our work. And you can see that we still have some, so we know the initial mass, we know H out, we know U initial, we know T surface. We don't know the entropy production at this point. But remember that in this problem, what we're trying to do is find the minimum amount of work for this process. What's the minimum amount of work? And we know that the entropy production has to be greater than or equal to 0. So to get the minimum, what we want to do is choose the case where sigma is 0. So the minimum amount of work coming in will be the initial mass times H out minus U initial. The minimum occurs when we have an internally reversible process. Right? So the minimum is when sigma is 0. And you can see that the more irreversibility you have, let's say as sigma is positive and gets bigger and bigger, so we have more irreversibilities, you can see that you'll get larger and larger amounts of work required. So the internally reversible case is really the most efficient case. So we have the numbers that we just previously calculated. We can go ahead and plug them in and find what the minimum amount of work is. So we said that the initial mass was something like 13.5 pounds mass. We found the specific enthalpy at the outlet and the specific internal energy initially. So when you plug everything in, it comes out to be 489 BTUs. All right, so there's one last thing that I'll do on this problem. Is it turns out we can work this problem a little differently. For example, if we wanted, rather than use the tables to look up the values for H out and U initial, I could make use at this point. Let me do it here. I'm going to go from here. I could make use of the definition of the specific enthalpy. Remember, the specific enthalpy is the specific internal energy plus pressure times the specific volume, right? And I'll do it specifically for the outlet conditions. So if I make use of that, so the work in minimum will be the mass initial times U out plus PV out minus U initial, right? Let me rearrange that to group the specific internal energy terms together. And then at this point, let me just focus on the U out minus U initial. Again, remember, for an ideal gas, the specific internal energy is a function only of temperature. But the outlet temperature is 70 degrees Fahrenheit, and the initial temperature is 70 degrees Fahrenheit. So that whole term, the U out minus U initial, is going to be 0. So this whole thing is equal to 0 since T out equals T initial. So then what we're left with is the initial mass times P times the specific volume out. And the volume of the specific volume of the material going out, when you multiply it by the mass, that just gives you the total volume. So this will be P out. Actually, I should have written that a little differently. There we go. So it'll just be P out times the total volume. So the work, the minimum work that we have to put into this is just the pressure coming out multiplied by the total volume of the tank. And again, the pressure at the outlet was 1 atmosphere, which we said was 2116.22 pounds force per square foot. And then the total volume of the tank was, I think it was 100, I believe it was 180 cubic feet. And so when you work out the numbers here, this comes out to be 38,100 foot-pounds force. Foot-pounds force is a unit of work or energy, so we could convert that to BTUs. And when you do the unit conversion, you could look that up on Google, what the unit conversion would be between BTUs and foot-pounds. It comes out to be 490 BTU, which is basically the same as the result we found previously, to within some numerical error. So it was just a slightly different way to approach this problem, just making use of the definition of the specific enthalpy. You get the same result regardless. All right, so this is a pretty good example that involves a lot of what we've learned so far. If you just kind of go back and recap what we did, we were dealing with an unsteady problem. This is a tank discharging kind of problem. We approached it with the first law applied to a control volume surrounding the tank. So we made use of the first law. We made use of conservation of mass. We made use of the entropy equation. And the reason we had to use the entropy equation was because we had a heat transfer term we needed to figure out. We also made use of the ideal gas law, as well as the ideal gas property tables. And also made use of the fact that the specific enthalpy and specific internal energy are functions only of temperature, as well as how a difference in entropy, specific entropy, how that is a function of temperature and pressure as well. So we made use of those ideal gas relations in the problem. So anyway, you can see that there's a lot of what we've done in this course all encapsulated into this problem. It's one of the tougher problems that we've come across. And then lastly, the one last thing I'll mention is we assume that we were dealing with an internally reversible process so that we would get the minimum amount of work for this problem. Any irreversibilities you can see will add to the work and mean that we'd have to put more work into the whole process. All right, so that concludes this example.